Thank you so much. HBK is a company that makes test and measurement equipment, specifically in this regard, power analyzers. And one question we get quite a bit from our customers or new customers or people who came from previous instruments were that for the same setup, the same operation, they get the same value for real power in their measurement, but different values for RMS, apparent power, reactive power. I'm not gonna lie to you guys, I went pretty far down the nerd rabbit hole on this one. But I think we give some really nice examples for how filters in an instrument can affect that and why you need to understand that from one instrument to another, you need to understand the filters to compare them apples to apples. So we'll go through that in some practical ways to get around these issues. Agenda, we're going to go through reactive power, RMS, harmonics and power, measurement and calculation, filtering effects. So reactive power and RMS fundamentals. We're going to start really basic. I promise it'll pick up, but for people here who might not understand power at the conceptual level as well, we're gonna start simple. So power equals instantaneous voltage times instantaneous current, and we're going to be speaking today specifically about AC power. So everything's going to be sinusoidal or pseudo-sinusoidal. So we have a voltage and a current in red and blue here that are perfectly in phase, the peaks and zeros align. And if we multiply voltage times current, we get a positive power, because positive times positive, that does not cross the zero line, which is my dotted zero line. However, this power has a cyclical nature to it. So it has a phase angle of 0, the power factor of 1, and we see this oscillatory power. Now, for a variety of reasons, this is hard to describe. It's got peaks, it's got frequency, it's got amplitudes, and also this is single phase, so it's a little more simple, but we'll stay simple. It applies to 3-phase as well. But this is all positive. But what happens when voltage and current become out of phase in an inductive or capacitive circuit? Inductive circuit being a electric motor, which is what I hope many of you are evaluating. Well, here's an example where we just added a 30-degree phase angle. Our power factor, which is the cosine of the angle, is 0.865. And these are all screenshots from our software. This is not meant to be a sales pitch, but it's just what I used. So we have a phase offset. Our peaks are now 30 degrees misaligned. Our zeros are now 30 degrees misaligned. And 30 degrees at 60 hertz is 1.4 milliseconds in time. So the phase delay is really a delay in time between when voltage and current arrive. So measure this with an angle. You could also measure it with time. It's just angle is frequency independent. But what we see in our power, when we multiply that V times I, again, we're sticking with real simple math, V times I. Our power, my black trace, now has this little negative segment. So we have some positive power and then some negative power. And this is oscillating power. So it does work and then it does negative work. Which we can't count that difference of the negative and the positive towards the active power. And many of you may have heard of reactive power or might be quite familiar with it. We'll talk about reactive power a little bit more. But this is the reactive power, is this negative oscillation. So now this becomes even more difficult to describe. We have this real power with a frequency and amplitude and this negative power. And what we get to is we end up averaging power. So that's where we go with this. But I think for the fundamental understanding, we start here. Okay, now purely reactive power, and this is really why I like to show this, is to highlight what reactive power is. So now my voltage and current are 90 degrees out of phase, so our phase angle is 90. Power factor is 0, which our little calculation tool gives negative 200 micro degrees, it's 0. And we get this perfectly oscillatory power. Again, V times I, but because they're perfectly offset, now peaks and zeros are aligned. We get positive power, then we get negative power. These cancel out to create 0 active power on the average. So when we average power over time, we get 0 power output. So this really is it's in a power line. It is there, but it's oscillating. It's not doing anything useful except creating heat and losses and all this stuff we don't necessarily want. So it's power that's showing up at the wrong time. It doesn't do real work because it's sitting there oscillating. And it limits how much power can be transmitted because it's taking up space in the power line. So it's really not as simple as real power. Real power creates torque, it creates heat, it creates light. It's phase-based. There's also a harmonic element. So this is purely phase-based power factor. We're going to talk about distortion power, which you can tell me isn't real, but mathematically it ends up happening. So we're going to treat it like it's real, even if it's debatable, because mathematically it shows up, which is relevant for why you get these different values in your instruments. So this is just a quick review. I'm not going to go through all the math, but I believe we distribute the slides so you can have all this fun math to determine these if you like. But again, we have that pure phase, zero phase angle situation where voltage and current are aligned, and we get power that's purely positive but oscillatory. We have that 90-degree phase angle where perfectly misaligned, so we have that oscillating power, which averages out to zero. And then we have the realistic situation of sub-phase angle in between, where we have an element of real and an element of oscillatory or reactive power. So I won't belabor this. I'm definitely not going through the math. We have a brilliant guy named Andrew Halfpenny who can go through all of this if you like. It's phenomenal to listen to. So that brings us to RMS, which one of the topics today is why are my RMS values different instrument to instrument? And what it ends up being is filter to filter. I'm not going to ruin any surprises. But the RMS is really, we take a sinusoidal signal, and rather than describing it with frequency, amplitude, wave shape, we can simply describe it as the root mean square. So the root mean square, if we take an average of a sine wave, it comes to zero. That's not useful. But if we square all the points and take the average, the square root of the average of those points, we get a really nice DC equivalent of what our waveform is. So for my sine wave with a given frequency and an amplitude of 5 amps, my RMS ends up being 3.5 amps. For my voltage with a 10 amp peak, my RMS ends up being 7.07. So RMS is really a really nice way to describe the DC. And for a pure sine wave, it's super convenient. This all gets flipped on its head when we start adding harmonic content. And when we start adding switching frequencies, it gets even worse. So from here, I'm going to show examples of the real world. This has all been pure kind of theoretical at this point. But it gives us a standard way to talk about AC power. It gives us a standard way to talk about waveforms. So these are very useful values if they're containing what we intend. And a lot of time we think that these are pure sine waves, but no, they're mathematical functions that take into account frequencies, harmonics. So we're going to dive into that now. So I think we've gotten out of the basics. Oh, sorry, we haven't gotten out of the basics yet. So again, just as a quick review, real power is what's doing work. It's measured in watts, voltage times current, the average over time. Apparent power, this is the RMS values multiplied by each other. It's agnostic of phase angle, so it's how much power there appears to be. And then there's reactive power, which is that oscillatory power that's not doing real work. And again, for anybody out there, you can think of it like a beer. Apparent power is the volume of the glass. Active power is the beer. Reactive power is the foam on top. So it's there. It's just not doing anything. Okay, so we've gone through the basics. We have a baseline. Now we can start talking about the topic at hand, which is harmonics and electric power, and really how they affect RMS, reactive power, apparent power. So again, review for probably many. A square wave or the sinusoids that we'll look at in inverter-driven electric machines are not perfect sine waves. In theory, a square wave is an infinite series of sine waves at different frequencies, basic Fourier decomposition. But we have a fundamental, which is kind of that carrier frequency, that main frequency, and then other frequencies which are imposed on top of it, which alter the total waveform shape. So we a lot of times will describe these waveforms as the fundamental and then some of the harmonic contents. But this is really important to keep in mind because each one of these harmonics, and granted, this is a perfect scenario again, has a phase between its voltage and current. It has its own element of reactive power. And those are getting added in, and those are getting added in, and those are getting added in. So when we talk about reactive power, we almost need to, also RMS values, we need to discuss the reactive power of what frequency band, the apparent power of what frequency band, the RMS of what frequency band. And this is the difference, and this is why filters become so important. Because if one instrument has a 3 kilohertz filter and one has a 30 kilohertz filter, you're going to see different values, because these harmonics have their own phase distortion. They have their own reactive element. They have their own RMS element that's getting added into the total. That gets even worse when we look at switching. And again, we'll get there. All right, so let's look at an example. Again, this isn't switching harmonics yet, but this is a practical example just to instill these points. So I'm taking another current and voltage that I've kind of manufactured in our software, just for example's sake, so I can operate in the ideal realm. So my current is, fundamental frequency has an amplitude of 5, and I implemented 5th harmonic and 7th harmonic with a given amplitude. Voltage is 10 volts plus a different amplitude of 5th and 7th harmonic. So we have strong presence of 5th and 7th harmonic. And we look at the waveform, and my current, is quite distorted. My voltage is quite distorted. But these are pretty realistic signals that we might see in a dirty system. And we look at the RMS value. We get 3.64 for current and 8.25 for voltage. This is that RMS calculation. Now, if we were to do the fundamental of, the RMS of just the fundamental value, we get 3.54 and 7.07 again. Same values we had last time. So we have to ask ourselves, which one am I interested in? Do I want the one without any harmonics? Do I want the one with the harmonics? So that's the question we need to ask is, I want the RMS value of what? So I'm leading to something which is the switching frequencies. But this is a question to ask, and this just introduces this basic idea of not all RMS values are created equal. It depends what our frequency range is. So now let's look at the power, instantaneous power. So the instantaneous power has that same frequency content. It's got that 5th and that 7th. There's a 30-degree phase shift in here. We see power reversals at the frequency rate of both of these. So we take these two frequencies, we phase shift them. We're getting harmonics in the power at the frequency rate of the voltage and current, which I find to be pretty exciting. And you can see we have this element of negative power, so we have that reactive power, but there's quite a lot of action here. Harmonics of the fundamental. So these harmonics introduce this distortion element. And what we see again is if we take the power factor of the total system, we get 0.827. If we take the power factor of just the fundamentally, again, that's 8.65. Which frequency are we interested in? And I think even more interestingly, if we take the power, so power is not immune from this either. If we take because the 5th and the 7th contain, the 5th contains negative power elements, the 7th contains positive power elements. If we take the power of the total frequency spectrum, we get 24 watts, or 24.8 watts. If we take the power of just the fundamental, we get 25 watts. So there's enough negative power in the 5th harmonic that we're actually making a decent, 4% of the total power is going to that. So this is another circumstance where we'll have people tell us, like, we get a different power value with your instrument versus somebody else's. Well, if you're filtering out the 5th harmonic in one instrument but not the other, you will see different power values. Even if it's just a little bit, there will be a difference, because which frequency band are you looking at? And again, I'm not going through math. I'm giving practical examples. If you want to go through math, please hit me up offline. I don't like doing the dissertation thing. But this is a real issue of which frequencies am I interested in? Because in theory, if I took this signal and I filtered it down to its fundamental, I'm going to see more power than is actually being produced at the output of the inverter. So that's instantaneous power. Now, getting into kind of RMS and reactive power elements of this, we take the same voltage, the same current, but now we do our RMS calculations and we see, VRMS, IRMS. We do our power calculations, reactive power, apparent power, power factor. In this example, I think it was a 50 kilosample sample rate, 50 kilohertz filter. And we go through the math, which is S equals V times I, RMS voltage times RMS current. We get 30. We take our power, which is instantaneous voltage times current averaged over a period. And we get Q by taking the Pythagorean difference of that to get 16.87 var. That's what we're measuring in this example. Now, if we go back to the definition of Q based off that power triangle, just that phase-based power triangle, we get V times I times the sine of theta, which is the phase angle, which if we take, 8.25 times 3.64 times the sine of 30.11, we get 15 var. Why is there a difference here? The difference is that phase angle is based on the fundamental. That phase angle is 0 to 0. But my signals have that fifth harmonic, that seventh harmonic, which have their own element of reactive power. They have their own phase alignment. So this V and I contain harmonics. We also need to account for the phase of those harmonics. We need to account for the power in those harmonics. So you can almost have to look at power factor in the circumstance with harmonics as power over apparent power. So that's another variable out there, which is, again, has that harmonic content in it if you leave it there. Okay. So now let's look at the fundamental, because fundamental is something that's very valuable to engineers. A lot of engineers ask for the fundamental, and we'll touch a little more on that. I introduced it earlier, but let's talk a little more about that. So the standard RMS and fundamental contain the harmonics. Each harmonic has its own RMS and phase. When we refer to the fundamental, we are referring to the first harmonic only. So we take that first harmonic only, and we again do our calculation for VRMS, V fundamental, IRMS fundamental. We see that difference in value. Same with power, same with apparent power. So now if we look at apparent power, we have 30 in the wideband, or the no filter situation. We have 25 in the fundamental situation. So there's a big drop there. For reactive power, we have 16.87 var, which drops to 12.5 var in the fundamental situation. So this kind of traditional equation is dependent on V and I being calculated on the fundamental or one individual harmonic. Fundamental RMS removes all of that harmonic content. It takes the frequency, it looks at just that first Fourier series transformation. We actually have in our software a package for doing that automatically. So it extracts all those harmonics out. And we get the reactive power calculation to be the same as we're calculating here. So you just really need to know what you're looking at. You need to know what you're calculating. These are math functions. They take what you input and they output something. So you need to understand your inputs. So fundamental is a really powerful tool for just looking at that fundamental main power carrying element. So if we look at kind of the fundamental versus the unfiltered, and this is just a table highlighting what we've already seen. Q and S and the RMS values have components contributing from the harmonics, and the same data gives you different values depending on what you calculate. So filtering has similar effects, and now I'm going to give some examples with switching frequencies, with inverters involved, where now, this becomes really, really apparent why this is such a big difference. Yeah, so also if we look at this, we can look at the power in that fifth harmonic, we can look at the power in that seventh harmonic. We can look at the RMS voltage and current in that seventh and fifth harmonic. And we can look at the reactive power and apparent power, because each one of these harmonics has their own elements of reactive power, of apparent power. So you can break it down to like understanding your values based on the harmonic content as well, which is a pretty interesting thing. If you're doing fifth harmonic injection, if you're doing third harmonic injection, you can start to understand the power quantities there, because it will affect your total output. So again, we just need to know what we're looking for. How many harmonics do we want included in these calculations? Okay, now we get into the inverter driven, which is kind of the question, or the inverter creates all the questions that drive me a little crazy. So here is just a standard inverter waveform, again, in our software, where we have a PWM voltage line-to-line measurement, a relatively low switching frequency, and we can see that current ripple affecting that. That the current has a really nice ripple to it. The voltage has those square waves, and I think you can imagine that if we multiply voltage times current, we get a pretty interesting power output. So fortunately, the motor acts as a filter to remove most of these harmonics from what we see at the shaft output. But this is actually a different example because it's a better example. If we take voltage, which here is in blue, inverter driven, times current in red, which you can see is pretty smooth. It's got some probably like fifth harmonic in there. And then we look at our power. That power is happening at the switching frequency. That power is oscillating at the switching frequency. Now, when we average the power, we get a really nice average. We get something like a 2.4 kilowatt average. It's very nice. But we have that really high frequency in the power. So if we look at the calculations, and this is based on, I think it was a 200 kilosample sample rate, or maybe it was actually no, this would have been a 200 kilohertz filter rate, so 500 kilosample sample rate. Our phase angle, again, this is of the fundamentals, because that's really the only way to calculate it, is 5.9, so relatively low phase angle. But our power factor is 0.311, because this is power factor calculated with all those harmonics. Power factor of the fundamental is 0.998. So what's the difference here? And the difference is switching frequency. And now we have the real power, which is the total power measured output, 2.27. And the fundamental power is 2.26. So, there's a couple of, 12 watts, 13 watts difference in the power. So there's not a lot of difference. It's very, very small, but there is a difference. So again, we need to, my fundamental has this much power, my total has that much power. There's a difference. So let's dig into this a little bit. So full sample rate calculations, 50 kilohertz, no filter. Apologize, I had it written down. And we see our voltage has this, again, the high frequency inverter. Our current has a little ripple to it, but relatively sinusoidal. Our power has those high harmonics. And if we run through and do all our calculations, S equals IRMS times VRMS, Q equals S squared minus P squared, we get the given values you see. 69 volts, 104 amps, 2.27 kilowatts, but absolutely huge apparent power and reactive power. We can see that we've got 7.9K VAR or VA and 6.9 VAR, low power factor for a relatively small phase angle. Now, if we look at a 10 kilohertz filter applied, so we apply a 10 kilohertz filter to voltage and current, so they have the same phase distortion. VRMS now goes from 69 volts RMS to 23 volts RMS. This is just by applying a 10 kilohertz filter. Now, I think what I didn't mention is that this is a 20 kilohertz switching frequency. So we're now taking that switching frequency out of the RMS equation, because again, we're just inputting it into a math engine. The math is doing what it does. We need to know what we're inputting. IRMS is relatively the same because it didn't change much. There wasn't a whole lot of inverter effect because the motor is a good filter. Power, pretty much the same. Reactive power and apparent power drops by 200%. Reactive power drops by 6x. The power factor comes to 0.899. And we actually the phase angle is improved as well because we take a lot of the harmonic content out. Now let's look at the fundamental, and we compare the 50 kilohertz, the 10 kilohertz, and the fundamental. And what we find is that 69 volts goes down to 21. So there is still a difference between the, we filtered out the switching frequency and the fundamental. And this is those fundamental-based harmonics. This is your 5th, your 7th, your 13th, your 11th. So again, we need to ask ourselves, where do we want that filter to get our RMS values? Or do we just want to operate with fundamental? Call it a baseline. IRMS, now we get a difference. 104.03, 104.03, 103.84. We've eliminated the switching, but now we're eliminating, again, those fundamental-based harmonics. So those rotational-based harmonics now. Power, there must be a little bit of 5th or something because P fundamental is, again, a little bit higher than P average and P filtered. Apparent power and now reactive power is the big one. We go from 6.8K to 113 volts amps reactive. Also our power factor 0.309 to 0.998. These are big differences just based on filtering. How many harmonics of the fundamental do you want in these calculations? That's the question. And I lay it out on a nice little table, and the questions are valid when people say, why is my measurement on one instrument different from another? Why is my MATLAB calculation different than my instrument? You have to, why is my scope different than my power analyzer? By like really drastic sums. Well, you have to ask yourself, what are you filtering at? Why is my model different? Well, what filter does your model have in it? How ideal is it? So this is the big question that I pose to people is, what are the filters? What bandwidth do you want to understand in these calculations? Because I can't give you the right answer. I can tell you why you're getting what you're getting. And I also think it's very interesting to see that it can affect power. This is only, 10 watts of difference, but 10 watts of difference is pretty significant. I'm going to skip it over the sales pitch. HBK sells instrumentation for measuring power. We have a lot of tools to help you analyze this stuff. You can take that offline with me if you like. In conclusion, reactive power and RMS are complex beasts. So please consider what values you want to look at and really consider that before you acquire data. I'm of the stance that take it as high as eliminates anti-aliasing. So, if you're switching frequencies at 10 kilohertz, measure at, 500 kilohertz and, filter at 200 kilohertz, eliminate all that electrical EMC, EMI noise, and then you can filter afterwards. But, do what's right for your test. I come from the particularly nerdy world. Make sure you're comparing apples to apples. Even if you have a variety of instruments, just make sure your filters are consistent. You're getting the same harmonic bandwidth. If you're measuring things with scopes or you're measuring things with your internal system, make sure your instrument matches your internal system. High frequencies cause reactive power, and whether it's real or not, the math gives you values. So, we can have a debate all day if it's real or not, but the math gives you these values that we need to account for when we're doing these calculations. HBK gives you equipment and expertise to help do these. And I would like to thank everybody and open up the floor for some questions.